Yo, yo, time to do some probability with our next free response. Let's jump right in. So, 2019, last year's exam. Here we go. Like, you did this already, right? Like, if you didn't, you should turn this video off, then try it yourself, then watch the video. Like, how are you going to make notes and corrections if you just copy my answers? Go do it. All right, anyways, assuming you have, here we go. So we want to tackle this problem. A lot of two-way table probability here. Always read through everything. One thing that's important, I think, to note is like question C here, you could do question C without even doing A or B, right? So again, we want to find every single possible like entry point we can to do something and show some understanding on the exam, right? Whether we do everything or not, right? We gotta do something. No blanks. I don't even know if that sentence made sense. But anyways, so let's jump right into part A here. So part A, we've got this two-way table summarizing some medical researchers' survey results, looking at how often or I guess how consistently people take medicine as prescribed based on whether they were male or female. So we're taking one person at random. So question A, what's the probability the person will be someone whose response is never and who is a woman? The only thing I'll really say about this is like, don't overthink it. Never and woman, right here, boom. That's the probability someone's response is never and they are a woman, right? So these 6.36% of people are the only people who are women and said never. So that is the end to A. Question B. I'm going to jump over to whiteboard, not this one. This one with my sloppily pre-made table here. So for question B, we now want to find what's the probability person is a woman or the response is never. So as we think about this, most common incorrect answer, you guys know I like to do that. Total probability someone's a woman, that's over here. So that's this 0.53 plus total probability someone said never, or total percent of people who said never, that's a 0.12. So then we get 0.65, done, if we want to have the wrong answer. So think about for a second, why is that the wrong answer? Like 65%, that's too big of an answer. How come? And so as we think about that, you could think visually. And so when I added 0.12, I'm really going to regret doing this to my table when I get to part C. 0.12, that's our total, right? 0.12 is these two numbers added together. And this 0.53 over here, that's the total for women, right? That's these three numbers added together. But you can see, right, when we add the 0.53, that's all these boxes, plus the 0.12, that's all these boxes, right? This got counted twice. And so we now need to subtract that overlap of 0.0636. So what we're doing here, this is what's called the general addition rule. Might sound familiar. Probability of A or B is the probability of A plus the probability of B minus the probability of A and B minus the overlap. And so for us, probability of never or woman is the probability of never plus the probability of woman minus the probability of woman and never, which is, that. So we got 0.12 plus 0.53 minus 0.0636. And that's it. I mean, I guess it would help if you could see what I wrote. Only other way I can think about going through it is you could just start to look at your table that I have totally destroyed and ignore the totals. So ignore those. Oh man, I'm going to really regret that for part C. And kind of just go through and be like, all right, which ones are a woman or never? So that's a woman or never because they said never. That's a woman or never because they're both. Not never or a woman. Yes, that's a woman. Nope. Yes. And so if I add these four numbers, these four cells in the table, right? 1, 2, 3, 4. That's all the never people or the women people, right? But now I'm not adding this twice, right? That's another way to go about it. So whether you try to use, not try, whether you successfully use the general addition rule, you could think about it formulaically, you could think about it kind of visually, the way I boxed in blue on the table, or you just go through ignoring the totals each individual cell and think which ones satisfy woman or never, right? That's how we're going to tackle that. Okay. Next up, question C here. Oh my gosh, I regret this so much. Question C is, what's the probability that someone says never, given our old friend conditional, that the person is a woman? And so in this case, for any conditional probability, remember conditional probability of like B given A is equal to the probability of A and B over the probability of A the way I wrote it. So it's always kind of both or the overlap divided by the given thing. So for us, when we go to approach this part C, we need to look at our numerator is just going to be never and woman, which was that 0.0636 divided by the total like given thing, which is the total for women, which was, I forgot, I want to say 0.53. Yes, 0.53. So this part C should be very obviously conditional probability to us because it says the word given. And so once we write this conditional notation right here, it just becomes a matter of plugging numbers into a formula essentially, right? Our numerator is never and women. The denominator is the total women, the total given thing, right? 6.36% of the 53% of women who I'm sorry, 6.36% of the 53% of people who are women also happen to say never. And that's it. That's how we do it. What's that equal? I don't know. 0.0636 divided by 0.53. Boom, 0.12. So this comes out to be 0.12. That's it. So jumping back over here to the actual free response. Let's see. The probability ones are easier to grade, right? Essentially correct if you got all three of them right. Partially correct if you got two of them right. Incorrect otherwise. Let's get those E's. Who cares how to get 9? No one's trying to do that. So question B here says, are the events of being a person whose response is never and being a woman independent? So for this question, there are many ways you could go about this. So we want to know, and this, by the way, is just the work we just did in part A3, I guess. So we want to know, are being a woman and saying never independent? So for part B, woman, never independent? I don't know. Let's find out. So there are a few ways we could go about this. One option, and this is probably what I would do if I were taking the exam, is to use the independence formula. So the independence formula says if the probability of B given A equals the probability of B, then events A and B are independent. And the reason I would use this if I were taking the exam is not really because it's easier or anything. It's just because I already did this, right? This is what we just did. So we found the probability someone says never, given they're a woman, right? That was that 0.0636 over 0.53. That was 0.12. So the reason I would lean towards this approach is only because I have some of the stuff, right? Half the math done. So what we want to compare that to would be, right, notice the B here is like the first thing. So that would be the total probability of never. So now what I can do is I can look at my table and look, what's the overall probability that someone said never? And if I do that, if I hadn't scribbled all over mine and erased it, we could see that the probability someone says never, in fact, is 0.12. So that means yes, these events are independent. So yes, being a woman and saying never are independent. because probability of never given woman equals the probability of saying never. Like, so the logic behind that is, and it's okay to write that sentence, like that's good, but the logic is overall there's a 12% chance someone's going to say never. However, here we're saying if I know the person's a woman, right? If I'm given the person's a woman, there's still a 12% chance the person said never. So knowing the person was a woman, right, had no impact on the probability the person said never. Or in other words, the fact that the person was a woman didn't matter. Being a woman and saying never are independent because there's a 12% someone says never chance someone says never overall. If someone's a woman, there's still a 12% chance they say never. So being a woman had no impact on saying never. So those two events are independent. So that's one way you could go about doing part B. All right. Another option, and you do what works for you. That seems unnecessary. We'll just do this. Another option is to use this idea that like and means multiply. So the probability of like A and B equals the probability of A times the probability of B if and only if A and B are independent. There's that fence from that box plot. So in this context, we could say, if these things are independent, the probability of woman and never should equal the probability of woman times the probability of never. If that works, then these events are in fact independent. Now from A1, we know the probability of woman and never was that 0.0636. From my table, the probability someone's a woman is 0.53. And jumping back to the table, the probability someone said never was 0.12. So if this works, then these events are independent. And if I do 0.53 times 0.12, I mean, obviously we should get the same answer that we got using the other approach. This does in fact equal 0.0636. So again, these events are independent. So what we're doing is we're checking, does the rule like and means multiply work? If it does, the events are independent. Right? So here I could say yes, being a woman, and saying never are independent. I mean, I could have gotten rid of the yes too. I could have just said being a woman and saying never are independent because the probability of woman and never equals the probability of woman times the probability of never. Sorry for the sloppiness. Obviously, you're not going to do the problem in both ways on the exam, but that's two different ways we could have done it. And honestly, there are others. You could have gone back to the independence formula, but instead of doing never given woman, you could have done woman given never to see if that equals the probability of woman. The only reason I didn't do this is because this would require, like, I don't know, we'd have to do two new things, right? We'd have to find the probability of woman given never, not that that's that big of a deal, and woman, right, and compare. And they would be the same number, but that's a third way you could go about it. All right. So going back to our rubric here. So for part B, essentially correct. We have to indicate the events are independent. All right, we got that. Give an explanation using the events in the problem. Talking about women and never, we did that. And justifying using numbers from the table, we did that. So you can see here, this is using that and means multiply idea. This is using the independence formula. The way we did it, this is the other way you could use the independence formula. And so they're saying, right, valid explanations with justification. So you could say, yes, these being a woman and saying never are independent because, and then write like one of these three bullets. All right, on to part C. So part C, I like this question because I like the fact that, you know, you don't need to know how to do A and B to do C. I would imagine, given the weird structure of this year's exam, I would imagine they're not, you know, they're going to try to have questions where each part is like standalone, meaning like, you know, maybe you could just do A and B and E or something, right? So that, again, you can have different ways to show what you've learned this year in AP Stat. So I wouldn't expect to see one question where A, B, C, D, E or whatever all build off the answer to A. So if you don't know how to do one, you don't know how to do them all. But anyways, who cares what I'm talking about now? So question C. Assume in a large population, the probability a person takes medicine as prescribed will always take medicine as prescribed is 0.54. We're going to select 5 people. We want the probability at least 4 will take the medicine as prescribed. Classic. So let's do it. There are my sloppy notes summarizing the question. So the first thing we want to think about is, what does it mean to say at least 4 people take the medicine as prescribed? Why aren't you answering me? Hopefully you said out loud at your computer while you were sitting home alone. At least 4 means 4 or 5 people take the medicine as prescribed. So there are a few ways we can do this. We could look directly at what's the probability, right? 4 or 5 people take the medicine as prescribed. 5 people take the medicine as prescribed. That takes us back to our basics, right? If you need to, right, draw 5 lines. This person takes the medicine as prescribed, and this one does, and this one does, and this one does, and this one does, right? And so that's going to be 0.54 times 0.54 times 0.54, or 0.54 to the 5th power. No big deal there. Or means add. Now, to find the probability that 4 people take the medicine as prescribed, that's going to be a little bit more complicated. Not a lot, just a little bit. Now, 0.54, that's the probability someone takes the medicine as prescribed. So that's going to be to the 4th power because we're finding 4 of them. The other 46% of people don't take their medicine as prescribed. That's going to be raised to the 1st power, because if 4 people do take the medicine as prescribed, that means 1 of the 5 people doesn't take the medicine as prescribed. But remember here that in green, this isn't it, because this only considers like one possible arrangement that 4 people take the medicine as prescribed. And so if you recall, this is that NCR or 5 choose 4 stuff, right? We have to find that number of arrangements. And so if we did on our calculator 5 NCR 4, it would tell us how many ways could you arrange 4 check marks on 5 lines. But we don't need that. Don't try to rewrite this mixing up all the 4 check marks. Just think about this one person who doesn't take their medicine as prescribed. Just think about this one X. How many different spots can that be in? That can be in 5 different places. So there are 5 different arrangements that we have to multiply by, right? 5 different ways, exactly 4 of 5 people could take their medicine as prescribed. So this is one way to get our solution. For many of us, I think that might be like the most understandable approach. But as we continue reviewing some calculator stuff here, another way we could do, right, kind of the same concept, we could go to our old friend binomial PDF, and we could say 5.54 comma 4 plus 5 comma 0.54 comma 5. So this is the same logic as what we've done in green and blue. If we type 5.54 comma 4, that's finding the probability exactly 4 people take the medicine. 5.54 comma 5, that's finding the probability exactly 5 people take the medicine. So the red binomial PDF stuff is doing the same conceptual, or taking the same conceptual approach as we did in green and blue, but just calculating those probabilities using, right, some calculator program, or instead of whatever, doing them out ourselves or whatever. If we're going to use this on the exam, if you just wrote that, you would get incorrect. So we have to label everything. So this is our number of trials. This is our probability that someone takes the medicine as prescribed. And this is our number, or I guess I'll say the exact number who take the medicine as prescribed. All right, so if I label those 3 things in context there, right, then I'm good. Or we could say number of trials, probability of success, number of successes, right? That's our NPX that we see in our calculator. But we have to label those things. Just like if we end up using normal CDF or inverse normal, whatever on the exam, right? We have to label those things. Almost done. So lastly, at least 4, right? That means 4 or 5 people take their medicine. So that's what we've looked at. We focused on, right, like the numbers of people we do want taking their medicine for this question. I've said phrase pretty poorly by me. The other idea is at least 4 or 5, that's everything except 3 or 2 or 1 or 0. Now, I wouldn't do like 4 separate binomial PDFs or 4 separate manual calculations for these red numbers, because why do that 4 times when you could just do it 2 times? But the reason we focus here is, if you recall, we can use binomial CDF for a cumulative probability or probability to the left. So I can now use binomial CDF, making sure I label everything, 5.54, and I want to cut off from here below. So I'm going to enter 3. This is going to give me the probability that 3 or fewer take their medicine, right? So this is the probability that 3 or fewer people take their medicine prescribed regularly or as prescribed. But that's not what we want. We want 4 or 5. So we can get the probability of 3 or fewer, but then we're going to have to subtract from 1, right? Because we don't want the red one, we want the blue one. And just like I said before, right, this is going to be our number of trials. This is our probability a person takes the medicine as prescribed. And this is what we're going to call our upper bound, right? This is like our maximum. So I might even say like the max number who take the medicine as prescribed. So that's another way you could do it. So you got 3 options. Never actually got the answer. Now it's on the next slide. So let's see what the scoring rubric's got to say, and then we're good with this free response. So essentially correct if we have 3 components. Indicates a binomial distribution with n equals 5 and p equals 0.54 when we're using binomial PDF, CDF, right? We're doing that. Indicates correct boundary value and direction. And reports the correct probability, like, that's just the right answer. Notice here in the notes, though, it does say this is cool. This does satisfy components 1 or 2. This is what we did, except here we left this off when we showed our work because there was only 1 arrangement. That's why we just wrote that 0.54 to the 5th. So we just had this. And then we didn't write 5 choose 4, right? I did mention that, right? But we just knew that there was going to be 5 arrangements. So we started with this approach and then moved into the calculator stuff. Notice here, right? This is super important, right? Label all 3 things, E. Label 2 things, P. Label no things, I. So don't forget those labels. All right, that's it. Have a good day, guys.